All right, folks, let's take a look at how we can manipulate some of these Taylor polynomials. First thing let's do is find the first three non-zero terms of the Maclaurin and the general term. Stuck that in there, for e to the x. Now this is one like sine you should have memorized. So if you don't have it memorized, you should pause me and build it. That's the only way you're going to learn to memorize this. Or you can fish through your notes, and that's a 2 factorial. That's just 2 times 1. So writing it as 2 is okay also. And the general term was this, and the series notation would have the series sign written in front of that, the sigma. Okay, now let's go for a challenge. Let's go ahead and find the first 3 non-zero terms in the general term for x times e to the x. Okay, so this is where we're going to have to do some work, right? We're going to need to do some building here for this polynomial. So we got some derivatives. I've got the function. Let's look at first derivative, second derivative, and I'm losing the focus here. Let me fix that. All right, let's get on with this. I had to adjust the focus, and I started writing some of the derivative notation down there. So let's go ahead and find the first derivative. This is a product rule, so the derivative of x is 1 times e to the x unchanged plus x unchanged times the derivative of e to the x, which is itself. All right, let's do it again. Derivative of this, derivative of e to the x is e to the x plus the derivative of this. Derivative of x is 1 times e to the x unchanged plus x unchanged times derivative of e to the x, which is e to the x. All righty, let's do it again. Derivative of e to the x is e to the x plus derivative of e to the x is e to the x plus the derivative of this is derivative of x, which is 1 times e to the x unchanged plus x unchanged times derivative of e to the x, which is e to the x itself. And then we got one more to do. Oof. Okay, and then the next step will be to find all these function values at the center and derivative values at the center. And this is a Maclaurin, so we're going to be centered at 0. So our center will equal 0. Okay, function value at 0 is 0 times 1. Okay, so that's 0. Function value at 0, this is 1 plus 0, which is 1. That's 1 plus 0, which is 2. I think I'm seeing where this is going. And that's the hardest part. Slow down when you do that, okay? And then we're just going to build this polynomial. Alrighty. So remember, first term is the function value at center, which is 0. And because this is asking for the first 3 non-zero terms, I'm not going to write this one, okay? You can write it and cross it off if it makes you feel better. Then I'm going to have to, so let's find this. X e to the x is going to be approximated by this polynomial. And so 0 is the first term. I'm going to leave it off. The second term should be the onesies. It's the first derivative value times x minus center, which is 0. So x to the first over 1 factorial. And then it's the twosies. Second derivative, x to the second over 2 factorial. And then third derivative, which is 3. X to the third power over 3 factorial. There's always 3 components to this. There's the derivative value, the power, the factorial, and I think we've hit the P4, right? First 3, oops, that's the first 4 non-zero terms. Okay, so sorry, I said first 3, but we'll just call this a P4. My bad. Alrighty, and we can simplify this a little bit if it helps you to come up with a pattern, but you don't have to. I'm just going to write it as x plus x squared plus, remember, 3 factorial is 3 times 2 times 1, so the 3's reduce out, so it's x to the third over basically 2, or 2 factorial, and this is 4 times 3 times 2 times 1. These cancel out, so you're left with x to the fourth over 3 times 2 times 1. That's 3 factorial, and so you can kind of come up with, those terms. Our general term, it looks like the terms are all positive, so I don't need something that makes it alternate. It looks like my power is 1 higher than my factorial. So I'm just going to rewrite it as in the easiest way I can. I'll let this be 1 bigger, n plus 1, and this will just be n factorial. And if you want series notation, we can go ahead and do the series notation. And I'll go to infinity here, and you just have to decide where you would need to start to get the first term being x, and that's an x to the first. So I think if I plug in a 0, I'll get x to the first, and 0 factorial is 1, so I get x to the first over 1. It looks like that's going to work. Remember, 0 factorial equals 1. It's the number of ways to arrange nothing, to visually differently arrange nothing. Okay, gosh, that was tedious. I really don't want to do any of that again. So there is actually a better way to do that. If we look up here at our original e to the x function, we could have done something very simple called a multiplication. So if we have e to the x and we want x times e to the x, it really is just as simple as taking x times the series. I'm used to ditto marks, right? So I'm just going to distribute an x through to everything. X times 1 is x. X times x is positive x squared. X times that is x to the third. And then x times that is x to the fourth. And you can even do it to the general term, right? We're absolutely capable of doing that. If we take our x to the 1 times x to the n, remember when you're, and this is my general term, remember when you're multiplying with like bases, you can add the exponents, which will give us x to the n plus 1 over n factorial. And if you look at what we did a whole bunch of work to get, it's the same thing, right? We got the same general term and the same terms, okay? They match. So take a second to look at that. So if you want xe to the x, you can just take x and distribute it through to your series. That's called a multiplication. And I'll write that here. It also works if I wanted this, e to the x divided by x. I could just take every term in this original series and divide it by x. Okay, that would be a division. I have other ones that I want to look at with you. Let's see, I could also do something like this, e to the 2x. Now, e to the 2x, that's not a multiplication. I actually changed what x was, didn't I? I'm going to pause this and adjust my paper. So in this one, I'm actually changing what's up in the exponent. I'm not multiplying, I'm changing the exponent. And if you notice that x is here and x is in all these places, this is called a substitution. You can find the series for e to the 2x without taking a bunch of derivatives. If everywhere you see an x, you plug in a 2x. So instead of this, I'll do 2x. Instead of this, it'll be, instead of x squared, it'll be 2x squared over 2 factorial. Instead of this term, x to the third, it'll be 2x to the third over 3 factorial. And yes, you can do that to your general term also. It'll be 2x to the n over n factorial. That's kind of cool, right? Way better than taking a bunch of derivatives. This is called a substitution. So you can't always do these things, but you can do multiplications, divisions, substitutions. You can even do a problem like this, where it just says e to the x minus 1. If you look at your e to the x series, you can just subtract the 1, and it looks like this. Getting rid of the 1, x plus x squared factorial. And so on. Okay, my papers are getting all blown around here. So what was I saying? Okay, so we can generate these terms. Now, when we look for the general term, though, we have to be careful when we're doing addition or subtraction, because a substitution was done to every term. And multiplying, we distributed the x to every term. The subtraction, all we did was take away the first term. So it does not show up in your general term. And if you look at this pattern, the powers and factorials are actually the same. The general term is the same as our term for e, right? You can try it out. The only difference will show up in our series notation will be where we start to generate the series without the 1. And if you check it out, if we want to start with the first term being x to the first, our n should really be 1 and not 0 as our series notation is up here. So there's just some subtle differences there, but be careful with the subtraction and addition. Those are just one-time things. So yeah, you can multiply, divide, substitution, some addition, subtraction, pretty much what you want. The only thing is there's no shortcuts for products of power series. If you're trying to take e to the x times sine x, think about that. An infinite number of terms, that's what we're doing here, sum an infinite number of terms for e, and distributing it to an infinite number of terms in the sine, that's going to be difficult. Or taking cosine times itself. Those are things that we have no shortcuts for, but we do have quite a bit of manipulations that we can do. Okay, folks, thanks.